Hi, hello again. We are working through the initial stages last time of a proof of the convergence rate of the Newton-Raphson method. So you've come across the Newton-Raphson method maybe one or two times before, but you probably haven't proved its convergence rate. We want to figure out whether it's first order or second order, that sort of thing. So it's going to be mainly working through the board today, but I want to work through the proof to get to a convergence rate of the Newton-Raphson rate method. So let's move to the board. There we go. Okay, right, so last time we did the Taylor series for the Newton-Raphson method. So we had this result that fx star, value of the function at the root, which is also 0, is expanded about xn. So if you imagine you're trying to start at xn and find the value of fx star, which is of course also 0, so we use that fact. And we had these terms the first derivative, and then the terms x star minus n squared. And last time I just did it as in terms of f double prime xn. I'm just going to substitute f double prime psi of n. Okay, and that subtle change is very important, because actually, so that's just rewrite that a little bit clearer because it's so important. That's psi of m. Okay, rather than x of m plus all the extra terms. Actually, all the extra terms are contained within this if we substitute xn for psi of n. So psi of n, remember, is anywhere in the domain of interest, whereas x of n is a specific point. When we make that thing, we have what's called Lagrange remainder. Okay, so that's the Lagrange remainder term, and it's based on a theorem that we don't prove, but the proofs are out there, that basically says you can write the remaining bit of the Taylor series instead of with x at n and all the other terms. So what we've done there, so we've replaced, let me emphasize this, x star minus n squared onto f double prime xm plus dot dot dot, all the extra terms. You can replace all of that by just substituting the variable in there. So it's a really neat analytical tool, a really neat theorem that we're going to use. So with this, and that's called Lagrange remainder. And now end of year 1 calculus, Matt had this in the notes when I last tutored it, so it may be that you came across this idea before and it's not the first time. Okay, so we're going to proceed with this term written as this. Okay, and that makes things really easy. The other thing to notice, and we observe that xn minus x star equals our error term, right? So we can now write f of x star equals 0 equals f of x of n minus e of n f prime x of n plus e of n squared on 2 f double prime psi of m. Okay, so that's Lagrange remainder theorem. And what we're getting towards is we had an expression with f's and f primes, and when we want to convert them into expressions in terms of error, en, and then we have this Lagrange remainder term. So we also had from last week this expression. Let me just dig it out. So this is our Taylor series. It gives us this expression, and then we have from the Newton-Raphson formula. Then we have this thing that error n plus 1 equals E of n minus f of x of n f prime of x of n. So we're basically going to substitute, if I call them 1 and 2, we're going to substitute and we're going to eliminate f prime from here and f from here to give us an expression purely in terms of errors, E of n. So, okay. So if we eliminate, sorry, we're just eliminating f of x of n between those two previous expressions. Okay, call them 1 and 2. We get this, so we get that 0 equals minus error n plus 1 minus error n f prime of x n minus E of n f prime x of n. So that was just substituting for f of n in the first expression here. And then we have a quadratic term in error, which is then at psi of n using our Lagrange remainder. Okay, so I'm writing quite big on the board because these equations are quite important, but then that implies that zero equals, so the term in E of n cancels, yeah, you can see that. It's got the term in E of n plus 1 remaining, and we're going to also divide through by f prime, so we're going to minus E of n plus 1, the remaining term, plus E of n squared on 2 f double prime psi of n psi of n divided by f prime of x of n. Okay. And just go to the next line. So that implies that e to the n plus 1 now equals, oh, sorry about that, e to the n plus 1 equals e to the n squared on 2 f double prime psi of n f prime x of n. So now we've with the aid of our Taylor series, we've taken our Newton-Raphson method that doesn't look anything like an error law to something that looks like an error law, like that. We've got the error at the new value and the error at the next value. And the key thing is this squared here. I'm just going to make it square on 2. So, and there's these coefficients. These can be just considered coefficients. F double prime for our convergence law anyway, and f prime of an xn. But the thing is, we've got proportionality here. So So the first thing we learn, we take the moduli, and don't worry too much about the coefficient for the time being, is that our absolute value of error is proportional to the squared of the error. So voila, we have, this is quadratic convergence, right? Let's just highlight that in red. So we got the squared law here. Whereas in the other two methods we've looked at, fixed point, bisection, it's just a linear convergence. So this means when your error is small, this is going to converge much faster than and that's the thing you can try in practical work, is the convergence much faster than bisection, say, which is linear. And I guess this is one of the main takeaway points from my module compared to last year, is that we now have done some analysis on these methods and we're able to put a label, if you like, on how fast it converges. We can say, oh, here's a method that converges linearly, and this one converges quadratically, and that's pretty fast convergence. So this is one reason why Newton-Raphson and Newton-style methods are so popular. Okay, so, but there's always a caveat here, is that it's dependent, and I have, as you can see, and I've only got to come back to it, I've sort of, for the time being, I've put aside this coefficient in gradients, f double prime and f prime. Now for this proportionality to work, this coefficient needs to, should we say, behave well. I'll define what I mean by that, but it means that the gradients need to work for so for example, f prime doesn't need to get too small. So you remember in our general convergence law, you had a coefficient a and you had a power q. So we've clarified that the power of q is 2, but the coefficient now is something dependent on f double prime and f prime. So let's look a little bit more at that. So can we formalize now this idea that Newton-Raphson is dependent on f prime and f double prime behaving well? Okay. And this is where our next theorem comes in. So we're going to have theorem 4 on the notes, is that we have this condition that f on variables f psi n f double prime psi n. This might seem a bit bizarre, this ratio, but it will fall out in the proof. It's less than 1. Okay, so we're saying the modulus of this product, f and f double prime, and the f prime psi n all squared, so that's mean all the square, less than 1. And you can see this, and this is violated. So we need that is required for convergence. Okay, I write it out a little bit more fully in the lecture notes, but that's all we need at the moment. But you can see, let's just have a look at that intuitively. You see if f prime psi of n is 0, so just, or tends to 0, is 0, this is violated, yeah. So we can see that this condition. So that's one example where Newton-Raphson just doesn't work. Let's just draw a little diagram to confirm that. If we have a root of a function there, but we have a local minimum. Okay, so that's x star, your root, and that's f. If we start our Newton-Raphson at this point, right, at if that's our xn, then of course the gradient is just 0, yeah? So it's going to go off either direction, it's going to diverge, it's going to know any of that root. Okay, that's an extreme example, but you know, it's a case worth bearing in mind. So this complicated condition makes sense, at least initially, and we want to just prove where it comes from. Okay, so and I think there may be time to start this proof, but I'll finish it off in the next video. So so the proof of this is so the NR has converged when psi n equals xn plus 1 equals x of n. Right, so I'm substituting my variable psi parent into the value of xn, but basically xn plus 1 equals xm when it's converged. So that if you substitute those into your Newton-Raphson formula, you get xn plus 1 and xn cancel, okay, and that gives then that f psi n on f that's just substituting into your Newton-Raphson formula. Okay, so that's the state of when your problem's each of the roots. Basically, if I now add psi of n onto each side, we get psi of n minus f of psi of n, f of psi of n equals psi of m. And if I call that g of psi of n, you can maybe start to be able to see it's a little bit like another problem we looked at. So what I've done is this is not a fixed point problem, but I've manipulated the whole thing into a fixed point form. Okay, so that's the key idea. So because I want to use the result from fixed point theorem to be able to show the condition for convergence for Newton-Raphson. So it's a little bit more involved, but it's understandable, I think. So we just added psi n, and then so we've got this problem that we've got this function g now, which is this thing, and then we can use fixed point theorem. So this is what I call this is fixed point form, not fixed point theorem because that has different convergence rates. But fixed point form, so we can use the machinery of fixed point theorem to prove what we need next. Okay, so that's a good time to pause. Obviously we're midway through this proof, but we'll again I'll try and restart, just for continuity view, just restart at least one line above where I stop in the last video, so you can feel you sort of caught up. And if that's obviously send me feedback about the level of overlap between each videos, but that's where I'm gonna stop it for now. Okay, so okay, this is me signing off, and hope that was helpful, and see you for the next video to continue the Newton-Raphson convergence rate condition. All right, see you then. Bye for now.